So we have a pipe here, and up to this point we have a entrance length, and after this we have a fully developed flow. If we observe the pressure versus length, then for entrance length this del P over del X is not constant, it is variable everywhere. But after the fully developed flow, after this point onwards, the del P over del X is constant, del P over del X is constant. Now once we have del P over del X is constant, then we can find out the head loss. So whatever formula we are going to develop for finding out the head loss, whenever fluid flows through a pipe or through other shape, some pressure is lost to overcome the frictional resistance, because we know that fluid offers frictional resistance because of the viscous effects. So we need to calculate this head loss as accurately as possible for designing the system. So first we are going to develop formula for laminar flow with the help of control volume approach or with the help of fluid element method. We have different methods for developing this formula. We can go for solution of Navier-Stokes equation for finding out the head loss for laminar flow or for turbulent flow, or we have the control volume approach. With the help of control volume approach also we can develop the relationship and we can find out the head loss. So we are going to discuss the control volume approach or fluid element approach for finding out the head loss. Right. Now we can also find out that what is the variation of the velocity at this section. How does it vary? What is the nature of this velocity profile? We can develop the relationship. We can find out what is U maximum, what is U average, right. So we can also find out what is the maximum velocity in the pipe, what is the average velocity in the pipe, what is the head loss. This is not head flow, this is head loss. Our aim is to find out head loss. Right. So here we have a figure in which we have a pipe, and at radius r we have a fluid element of length L, and this fluid element is shown here. If we are showing it in a separate figure, then we have to show it with the help of free body diagram. Free body diagram means we have to show all the forces coming on this fluid element, right, on this fluid element. On this fluid element, at this point we have pressure, let us say P1. So what is the pressure force at this point? Means on this phase. On this phase the pressure force is equal to P1 multiplied by area, and on this phase what is the force due to the pressure? The force on this plane is equal to P1 minus del P. What is del P? Del P is the pressure loss between these two sections which are situated at distance L. So P1 minus del P, and this acts in opposite direction because we have stated that pressure always acts in such a manner so that it compresses the fluid. So this one is acting in this direction and this one is acting in this direction, though this fluid element is moving in x direction. So P1 minus del P into area, and this del P is lost to overcome the frictional resistance. And on the periphery we have the force due to the shear stress. On this periphery we have a shear stress of magnitude, let us say tau, then tau multiplied by the peripheral area peripheral area is equal to pi d into L or 2 pi r into L. Since we are interested only in x direction, that is why we have not shown the weight of the fluid element which will act in downward direction, and we can find out the weight also, but we are interested only in x direction, that is why we have not written the weight component. Now, since flow is in a steady condition and it is fully developed, there is no acceleration effects, no inertial effects. It means that these forces which are acting on this face and on this whole periphery, they are in the balanced condition. So, summation of forces in x direction must be equal to 0. So, with the help of this simple governing relationship principle, that under steady condition summation of forces in x direction must be equal to 0, we can write this relationship P1 multiplied by pi r square, this force acting in x direction, this force acting in negative direction. So, this is negative P1 minus del P pi r square minus this shear force is acting in negative x direction. So, this is minus tau 2 pi r L shear area 2 pi r L, this must be equal to 0. So, with the help of this equation which is developed on the basis of summation of f x is equal to 0, we can write del P over L is equal to 2 tau divided by r. Now, this relationship is developed at radius r only. So, r is a variable here, and corresponding to that r we have the shear stress, and this del P is function of radius or del P is function of length? Del P is function of length, here, right. So, del P and L, del P is the pressure loss for distance L in x direction.